back. I am Dr.N.Uma working as Associate Professor, PG and Research Department of Chemistry, the Standard Fireworks Rajaratnam College for Women, Sivakasi. Dear learners, today we are going to see about the experimental verification of Debroglie's equation. As we learned in the previous session, just a recap of Broglie's postulate. It states that the particles also have wave nature, the total energy E and momentum P of an entity for both matter and wave-like is related to the frequency mu of a wave associated with its motion by Planck's constant E is equal to h nu, and we derive the Debroglie's equation as lambda is equal to h by p. This is the Debroglie relation, and it predicts the wavelength of the matter wave lambda associated with the motion of a particle with momentum p. Let us enter into the experimental verification of Debroglie's equation, which was first put forward by Davison and Germer. This experiment demonstrated the wave nature of the electrons, confirming the earlier hypothesis of Debroglie. Electrons exhibit diffraction when they are scattered from the crystals whose atoms are spaced appropriately. In 1927, the American physicists Davison and Germer determined the wavelength for slow electrons accelerated under small potential difference and gave the first experimental evidence for the existence of matter waves. Let us see the experimental setup for Davison-Germer in the next slide. This picture gives you an idea about the experimental setup of Davison-Germer experiment. Let us see the components present in the experimental setup. Number 1, the electron gun. It consists of a tungsten filament F that produces electrons by the process of thermionic emission. The second one is the high tension battery B2. It provides suitable potential difference to accelerate the electrons. There is a cylinder A to provide a fine beam of electrons, and there is a nickel crystal placed which acts as a scatter. It is capable of rotating about its own axis perpendicular to the plane of the paper. Next, we have to collect the electrons. So, we have an electron collector capable of rotating about the same axis as the nickel crystal target. So, it collects the scattered electron beam in a given direction. Next, this experimental setup is connected to a galvanometer, and it is also connected to an electron collector. The deflection in the galvanometer will be proportional to the intensity of the electron beam. Then there is an evacuated chamber C, and it encloses the entire apparatus. What is the theory? Initially, the electrons are accelerated under a potential of about 40 volt, and this potential difference is increased in small steps to perform the experiment at different fixed values of potential difference. The beam of electrons is made to fall normally on the crystal. For each value of potential difference, polar graphs are drawn between the angle theta and the collector current. Angle theta, known as co-latitude, is the angle between the beams of electron on the nickel crystal and that which enters the electron collector. The curves obtained corresponding to different accelerating voltages are shown in the figures. A smooth curve is obtained for a potential difference of 40 volts. let us see the 40 volt curve. It shows a smooth curve. The next curve, which is shown for 44 volt, gives you a bump at the starting point. So, a pump begins to appear on the curve and this bump moves upwards with increase in accelerating potential difference and becomes most prominent at an accelerating voltage of 54 volt and for theta equal to 50 degree. Beyond 54 volt, the pump decreases and is lost completely at about 60 volt. So, we can visualize these changes in the pump height on this figure. Hence, the most prominent maxima observed corresponding to the accelerating potential difference of 54 volt at angle theta is equal to 50 degree with incident electron beam gives a strong evidence that the electrons are associated with waves which after reflection from regularly spaced atoms in nickel crystal give constructive interference as in the case of Bragg's X-ray diffraction from crystals. The collector current is maximum at the co-altitude of angle theta, which is equal to 50 degree we told earlier, corresponding to the volt when the accelerated electron beam is made to accelerating voltage V is equal to 54 to fall normally on the crystal. As shown in figure, the incident and the scattered beams of electrons make an angle of phi is equal to 65 degree with Bragg's planes. The separation d between Bragg's planes can be determined by using X-rays of known wavelength lambda and applying the Bragg's equation 2d sin phi is equal to n lambda. The value of despacing d for nickel crystal used in Davison-Germer experiment was determined to be equal to 0.91 angstrom. Now, the wavelength lambda of matter waves associated with electrons can be calculated from Bragg's equation by substituting the value of phi as equal to 65 degree. So, what do you obtain? D is equal to 0.91 angstrom and n is equal to 1. Therefore, we get the value of lambda as equal to 2 into instead of d 0.91 into sin 65 degree, or we get the value as lambda is equal to 1.65 angstrom. But from Debroglie's equation, the wavelength of the accelerated electron is given by lambda is equal to 12.27 divided by the square root of potential difference angstrom units. When accelerating voltage is substituted as 54 volt, we get the value of lambda as 1.66 angstrom unit. So, comparing the two values, the one above this equation which is underlined and bold with the value lambda is equal to 1.65 angstrom and the value we got upon substituting the value of potential difference in the Debroglie's equation as 1.66 angstrom. So, they are equal, almost equal. So, this experiment gives an excellent agreement between the two values of the lambda. Therefore, Davison-Germer experiment verifies Debroglie's hypothesis that the wave nature is possessed by particles in motion too. Thank you for your patience listening. We will meet in the next module. Thank you.